Okay, so next one we'll actually be expanding on the measurement of time, and we'll learn about rate as well for this subtopic over here. So the thing is, time is basically just a quantity, that is how many times something repeats itself over a period of time. So no, let me phrase that wrong. So it's just the period that an activity happens or something that you're measuring happens. Okay, so SI unit, which is the standard units for time, is in seconds. So your time, now typically for time we use letter T, we can say like 20 seconds. Okay, so the thing is, because we typically use the stopwatch, so we'll put it in 1 decimal place or 2 decimal place itself. Sometimes you might see hours, you see minutes, you see years. So you need to be familiar with all your conversion. So previously, when we were learning about the unit conversion chapter itself, especially the kilometers per hours, meters per second, those that involve time, typically we actually use this conversion over here. Now, some of your stopwatches that you see over here, these are actually in different units. So if you see this one is in minutes, this one is in seconds, and this is actually 1/100 seconds. Okay, so how do we read this over here? This is actually 5 minutes, 53 seconds, and 62/100 seconds. Okay, so this is not milliseconds, don't make that mistake. So how do we solve this? We will leave it as it is, and then we'll plus. So this one, 0.62. So you end up with 353.62 seconds. Now, for this one, we don't need to round up because this is already in the correct format. So it is how you read this reading over here. Okay. So similarly, for this one, you can see that it gives this one, some of your stopwatches are a bit more clearer. You actually write the hours, the minutes, seconds, and 1/100. So this one is a bit hard to see, but it's 1/100 seconds. Okay, so how do we read this one? We do the same. Time is 16 minutes plus 10 seconds plus 13/100 seconds. That's how we read this. So bracket 16 times 60, and this is 10.13 seconds. When you write second, all of these is seconds now. So you press the calculator itself. 16 times 60 plus 10.13, you end up with 970.13 seconds. So this is a very, very large number. And if you notice, the seconds I write is typically smaller than the number itself, because if you write seconds like this, it looks like 5. So you write my seconds at the bottom right-hand corner. So this is how you read it. So you have this. So in this format, leave a space as well so that you know that this is your units. Because some of us, our handwriting may not be the best. So because of this, do take note. And this precision up to 0.01, so either 1 decimal or 2 decimal place, you need to double check with your school, which one do you use. Check with school. Okay, so if you're not sure, you can always use the 1 decimal place. Okay, so if let's move on to your next page. So let's move on to the next page. Let's talk about your pendulum. Now, previously in the previous video, I actually mentioned about your pendulum and how we measure the number of oscillations or the number of cycles, right? So first things first, let's go into the detail of what exactly is a pendulum in the first place first. So a pendulum is just any object that's suspended from a fixed point. This is your fixed point. Okay, so we have a weight, which is called your bob. So this thing, oops, hang on, this is what we call your bob. Okay, so you actually move from A to B, B to C, C back to B, and then B back to A. Okay, so basically we usually start here and we'll end here as well. So what it means is 1, 2, 3, and 4. So basically you move back and forth. This is one cycle. Okay, so this entire thing is one cycle. So you need to be careful. One cycle is what we call one oscillation. Okay, the movement is called oscillate as a verb, An oscillation is your entire process. Okay? And we have a special name for the time taken for one oscillation. It's called your period, like a period of time, right? So this period, either we use small t, but more commonly we'll use big T. So most of the time you see this letter X over here. This is just a large number. So usually it's 10, 20, or like bigger numbers. You can even go to 50 or 100. Okay? So really, really depends on the question itself, how accurate you want your reading to be. Or some questions itself, the school is nice enough to actually give you the exact number of what you need. So as you can see, if you have 20 oscillations, the time taken, let's say it's 20.20, you will just divide using this formula, and this is the time taken for one oscillation. Okay, so you move back and forth, A to B, B to C, C back to A. Like basically this one process, A, C back to A, is 1.01 seconds. It's very, very fast. So we will have to take multiple oscillations, because if you take only one, you will make a lot of mistakes. Your error will be very significant. Not a lot of mistake. Your error will be very, very significant. Now, what is this frequency over here? This is how many times, how many oscillations in 1 second. Okay, so basically how many times something repeats itself in 1 second. So if you clap your hand, if you clap every 1 second, you clap one time, your frequency will be 1. So this one don't need to worry too much. This one is mostly FYI. Okay, but just double check if your school does cover this, do read up on this. But most of the time it is something that is more additional for your IT schools only. So you just need to check if your school covers it or not. Now your amplitude, you have a new term, amplitude is your max distance from your original position. So this is your max distance. Okay, so this distance is your amplitude. It's not your diagonal distance, it is the horizontal one. Okay, so next, we have your pendulum over here, right? So this is your side view, this is the front view, and basically this is what it looks like. So typically we have this retort stand which clamps onto a cork, and then there's a strap in between the cork over here. Okay, so basically we just want to measure your length from the bottom of the cork all the way to the middle of the bob or to the top of the bob itself. You need to double check. Your length is all the way down here. Okay, so this golden thing is what we call a bob. Okay, so this one, the way this person is measuring it is actually wrong, because if he does it like this, you see that the line that is measured is actually diagonal, which is incorrect. What you should be doing instead, let's hope my ruler is working. Yes, you should be measuring straight like this, rather than what he is doing over there. What he's doing is slightly off. You should be measuring like this. Okay, so just place it like this. Even if the bob is in the way, just make sure that you are along that line. Okay, so moving on. Going back to the diagram itself. Okay, so for over here, some schools will mention this, some schools expect you to memorize this formula. Okay, now if you look at the formula over here, you have your length, and this is how strong my gravity is. So this one is a bit special. Just know that G is always there. Okay, so don't worry too much about this one. So the thing is, typically we'll use small angles of oscillation. Now, if you notice in this formula over here, there is no mass, right? There's no M, there's no small letter M over here. So what does that mean? M does not affect T. Remember, period is T. So mass does not affect T. But if you notice your L is inside, right? L will affect your period. So what does that mean for this? More L, more T. Which makes sense, right? Because if your string is longer, or in this case, if your string is shorter, it will move a shorter distance. So you should technically take less time to move, right? If you compare to the longer over here, right? So by having a shorter length, you will have less t. If you have a longer length, you have more t. And similarly, if you look at your g, g also affects your period, which kind of makes sense because it's like what is causing you to move back and forth is actually the gravity that's pulling the bob down, causing it to swing back and forth over here. Okay, so the thing is, why are we using small angles of oscillation? Because we are actually using minimizing errors. Okay, because sometimes when you swing such a big object, right, what happens is, let's say this is the top view. When you swing back and forth like this, by right, you are supposed to swing like this. But in actual, when you actually swing back and forth, what happens is that it might actually form like an oval shape. So the thing is to avoid making a very big circle, like a very big oval shape, right? You want to just use a very small angle so that when it actually moves, it doesn't make that big of a difference. Okay, so that's why we use small angles of oscillation. The purpose is to avoid swinging in a circular motion. And next one is one of the more special one. We actually start after a few oscillations, because when you first swing the bob, right, sometimes you might be pushing it, so you want it to stabilize first, so that you can measure it. So you can see over here, down here, the first few might be faster or different. So that's why we want to wait. So we let it swing back and forth. Then when it reaches the very top or at the middle, depending on your school, then we start the stopwatch. Okay, so every time you want to calculate your oscillation, 1, 2, 3, 4, 5. Every back and forth, we count slowly 1, 2, 3, 4, all the way to whatever x value that we have. If we have 20, we'll count all the way to 20. So you'll take about 20 plus seconds. Then you have your reading itself. Okay. Then moving on to our human reaction time error. This one is the error that we previously mentioned. That's why we take readings for a large number of oscillations. This is x. Okay. And then we will take the average to determine the actual period. This is to reduce error. Okay. Oh, hang on. I placed it wrong. It should be at the here. Okay, so we do this to avoid error. Okay, we take average to avoid error. This side, like this. Okay, so just take note, our lag itself, our human reaction time error is about 0.2, 0.3, 0.4. Everybody has different reaction time errors. Okay, so unless you're professionally trained, you can reduce your reaction time error, but basically for normal humans like you and I, we will actually have about 0.3, 0.2, that kind. So if you notice over here, if we only measure 1, this is what we measure. The error is this much. This is the actual value, right? But your error is 33.3. That's like 1/3 of your reading itself. So you actually made the error that is 1/3. So it's like if it's an exam, you only have 67% left, which is not good. Okay, but on the other hand, if you take 20 oscillations instead, you measure 18.3, and then you minus away the error. This is what you calculated. This is for 20 oscillations. So if you actually divide by 20, your number will actually be closer to the correct value itself. Okay, so basically, this is for one reading. It is 0.9 seconds, right? Then for this one, we'll take 18.0. Okay, so you can see the error is much more significant. This actual is supposed to be 0.9, but you measured 1.2. Okay, so same thing. And for the one below, instead, 18.3, we divide by 20. we get 0.915 seconds. So if you compare these two, which one is closer to the correct value? Obviously, it is our second one. So this one is no good. That's why we actually use 20 oscillations, because our final result, when we actually calculate the correct, try to solve for the correct value, having this minimize the error itself. So we only have a small error. So we will actually be closer to the 0.9 seconds. So this is how I explain. By taking the average of multiple oscillations, I can reduce or minimize the human reaction time error. So as the number of oscillations increase, the error will decrease. So the more you pick, the closer and closer, the closer the value is. So even if you want to get even better or even more accurate results, you can do 30 oscillations, 40 oscillations, 50, even 100 oscillations. So if you actually calculate it properly itself, you will notice that your values will be very close. Therefore, you'll be more accurate compared to if you only take small numbers of oscillations. Okay. Now, basically, rate. Rate is slightly different from your time itself. Rate is actually comes from the word ratio. Okay. So it is actually comparing two physical quantities. So how does one change as the other? So for example, your speed. Speed is distance over time. So what does that change? So what does that mean? So your speed means as time increases, how much does distance increase? Basically, that's what it means by speed. If you are fast, your distance will increase much more. Okay. So let's take a look at this question itself. You have a flow rate of 120 cm cube per hour. So what does that mean? 120 cm cube takes 1 hour. Okay, or you can write it the other way around. 1 hour means this. So now the question is asking you in meter cube. What is 125 minutes? So the first thing we can do is 120 cm cube. Let's change it to meter cube first. 120 times 1 cm cube. So 120 times 1 times 10 to the power minus 2 cube. So you end up with a very small number here. But take note, this is not a final answer. This is meter cube. So this is for 1 hour, right? And 1 hour is how many minutes? 1 hour is 60 minutes. So now, 60 minutes is equals to 0.000120 meter cube, right? So if I want to change to 125 minutes, what do? I will times 125 and I divide by 60. So this means 125 over 60, you get 0.123250 meter cube. Okay, so you can use your math to solve. Most of the time, rate is actually mostly math. You just need to be able to identify the relationship between this and that. Okay, now next one over here, you have a rate of consumption, 10 kilometers per liter. Okay, that's not IR, that's liter. So they tell you volume is 75 kilometers. So 1 liter, hang on, 10 kilometers, I use 1 liter. So they want now 75 kilometers. How many do I use? Over here, we times 75 over 10. Over here, we do the same, we times 75 over 10. So we use 7.5 liters. That's all. Okay. Next one, motion map. Basically, this is a way to tell us how an object is moving. Now, all these person that you see, they are actually the same person. So this is basically different pictures. So it's like you take a camera, different time. So every second, he moves a distance d. And if you notice, the distance here is about the same. So he's moving at constant distance and speed. So it's constant speed, basically. Okay, and if you notice in the second one, he's actually getting further and further away with every second. So what does that mean? He is actually getting faster. Okay, he's moving faster. So what does that mean? My speed is increasing. Okay, so just take note, basically from this, you can actually identify if it's moving faster or slower or whatsoever. Now, next, I'll introduce to you what is called a ticker tape timer. This is a ticker tape timer itself. Basically, this, hang on, this thing over here will actually move up and down. And basically, it will just punch a hole. You can imagine your ticker tape timer is a hole puncher that is doing it at a regular interval. So every now and then, at a fixed timing, it will actually poke the hole back and forth, back and forth, back and forth, back and forth until there is a pattern that is formed. Okay, so basically, this hole puncher will move up and down. While meanwhile, I have the tape over here. I'll be pulling the tape, so every now and then you'll poke a hole. Then because I'm moving the tape, you'll poke the hole, poke the hole, poke the hole. It's actually moving in this direction. Okay, so basically this is how it works. Now, if I tell you it is 50 dots per second, what does that mean? Now, you don't have to use what I wrote here. You can also write, okay, so 1 second, I have 50 dots. Or it can be the other way around. 50 dots, arrow, is 1 second. So 1 dot is 1 over 50 seconds. It is 0.02 seconds. So you can see every time, every 0.02 seconds, I make a new hole. Okay? So let's try to do problem solving. Now, first thing first, speed. You're right, it is distance over time. Okay, so first things first. Whenever I have a formula, first thing I do is, what's my distance first? Let's solve the distance. Distance is 12 cm. Right? And then what's my time? Now, this is the tricky part. What is time? So the thing is, whenever we are doing this kind of motion map or ticker tape timer itself, the first dot is considered 0 because time is 0 here, right? So the thing is, it is produced 50 dots per second. Now, it's not always 50 dots per second. It's just a number I use commonly. Okay, can be 10 dots per second, can be 20 dots per second. It really depends on the question itself. So the thing is, we don't do that first. 50 dots is 1 second, right? So how many new dots do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We made 10 new dots over there. So 10 dots. What do? We divide by 5, right? So this side also divide by 5. So this is 0.2. So what's your time taken? I took 0.2 seconds to make 10 dots and travel 12 cm. So what is my speed? Now, if this question doesn't say express it in meter, in SI units, we can just take this, divide by this, you end up with 60. So 60 cm per second. Okay, so just take note, if you need itself, we can actually change it here. Because I have the C, I will times this, it will be 0.12 meters. So if I have this, I will have 0.120 over 0.2 0.60 meters per second. Okay, it's exactly the same, just take note of the units. That's why your units is very, very important. You need to write everything down. Okay, now next one, your ticker tape timer. Same thing, I'm still using 50 dots because I'm very lazy. I just typed it in. So the thing is, you have different speeds, right? So we'll separate them, car 1 and car 2, and they tell you it must be meters per second. So first things first, 50 dots is 1 second. Okay, first, let's identify 0, 1. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 new dots. Okay, so let's solve the time bit by bit. First, 1 dot. How long does it take? 1 over 50 is 0.02 seconds. 10 dots. How long does it take? 1 over 5, it will be 0.2 seconds. Okay, Then let's solve car number 1. So your distance was 20 cm. 20 cm, we will times 10 to the power minus 2 meters. We get 0.20 meters. The time is 0.02 seconds. So your speed of car 1 will be 0.20 over 0.02. Okay, you will get 10 meters per second. Now for your car number 2 over here, we do the same thing. You have 90 cm. The time is 0.2 seconds. This is 0.90 meters. So your speed. Now speed we don't write as, so speed would be 0.90 divided by 0.2. So you end up with 4.5 meters per second. So your car 2 is actually a little bit slower compared to your car number 1 over here. So because of that, you can see the two differences in the speed, and therefore you have different values over here. Okay? So if you want to use the ratio version will look like this, but the calculation-wise is almost exactly the same. So you don't need to worry too much about this part. You can use the arrow method. If it's clearer to you, feel free to do so. Okay?